What is a quark really? If it is not just a tiny abstract point in an equation with no size, no structure, and no picture your mind can grab onto. In the energy filament theory, a quark becomes very concrete. It is one of the smallest and most unstable filament rings in the universe, and it carries a straight tension pattern that is strongly biased to one side, a built-in asymmetry that makes a single quark almost impossible to keep alive on its own for more than a fleeting instant. Picture dropping a very small filament ring into the energy sea. If the ring is wounded symmetrically so that the tension inside and outside is nearly balanced, the straight texture it carves in the sea is also fairly even, and the energy sea feels this as smooth and low cost, which is part of why an electron can hang around as a long-term resident of the universe. A quark, by contrast, carves a straight texture that leans hard in one direction, like a rubber band pinched into a lopsided loop or a hair tie twisted into a strange little knot. You can hold that shape with your fingers for a moment, but the instant you let go, it wants to snap back into something more natural, because the tension on one side is doing far more work than the other. In this language, a quark is unstable from birth because of that asymmetry. The tension on the inner and outer sides of the loop is badly unbalanced, so the energy sea keeps tugging harder on one side to fix the mismatch. And an isolated quark appears quickly and collapses just as quickly, like a fragile top knot of hair that a light breeze can undo, or a bent paper clip that never quite wants to stay in the shape you forced on it. Yet in our equations we keep talking about quarks inside protons and neutrons, and we say there are 3 of them in each. So the mystery is not, do quarks exist, but how do such unstable rings manage to hide inside stable particles? The trick is that 3 quark textures can complement one another in a very specific way. Think of 3 oddly shaped puzzle pieces. Each one by itself looks wrong and jagged, with edges that seem to stick out in the wrong places. But when you rotate them and fit them together, the bumps and gaps interlock, and the outline suddenly looks neat and balanced. For quarks, those 3 asymmetric straight textures twist into a stable 3-bridge pattern in the energy sea. 3 thin bridges of tension tie 3 tiny rings into one locked structure. Their individual leaning patterns push and pull against one another like the 3 legs of a tripod. So the whole object sits in the sea like a small 3-legged peg driven into soft ground. Hard to tip over and much cheaper in tension costs than any of the pieces alone. Now imagine trying to yank one quark out of that tripod. As you pull, the 3 tension bridges do not simply snap cleanly. They are stretched straighter and tighter, the tension costs climbs. And it becomes like trying to break a tough rubber band by pulling it longer and longer while it resists harder and harder. From the point of view of the energy sea, letting a bridge simply tear is extremely expensive. So the system chooses a cheaper move. It spins up a new pair of tiny filament rings in the stretched region, a new quark and antiquark pair, and reconnects the bridges so that you end up with new bound combinations instead of a lonely quark. The harder you try to isolate a quark, the more composite objects you manufacture. Which is why high-energy experiments see showers of new particles but never hand you a single free quark on a plate. This is quark confinement in this picture. It is not that quarks are locked in a literal box with solid walls. It is that the structure of the energy sea never allows a lone quark configuration to stay cheap, and any attempt to pull one out automatically triggers the creation of new rings that constantly repair the 3-bridge pattern and keep the 3 at a time rule in place. What textbooks call color charge 3 abstract colors that must it up correctly becomes a simple geometric idea here. The 3 colors are 3 complementary directions of those asymmetric straight textures. 3 different ways the straight pattern can lean. And the little fortress made of 3 quarks is only stable when all 3 directions are present so that the combined tension pattern looks balanced to the sea. If one direction is missing or repeated, the asymmetry is exposed again. The tension costs jumps, and the little fortress prefers to fall apart and recombine into some smoother structure with all 3 directions properly filled. This is why nature seems obsessed with quarks in 3s and never in 2s or singles. So we can wrap it up in one plain, visual sentence. A quark is not a mysterious structureless point. It is a very small, very unstable filament ring with a strongly one-sided tension pattern, and a single quark is like a rubber band forced into a crooked loop that always wants to snap back. Only when 3 such crooked loops point in complementary directions can they lock into a stable hole. And that hole is what we recognize as a proton or a neutron. The sturdy building blocks of ordinary matter that quietly hold almost all the masses in your body and in the stars. Tap follow, share it on New Physics, Clear Universe.